So, hi everybody. Thank you for this introduction, and thank you so much for inviting me to present how ML is used in the detection of exoplanets and to share my work at KX here today at this event. I'd say that most of you don't know much about KX or have never heard about it, so I think it's fair if I start my presentation giving a brief introduction to it. Especially because I use our own product to solve the problem that concerns us today, and it will help you to better understand our approach to the solution, and if you know better about us. Basically, we are a technology company, global technology company, who has offices in many different locations around the globe. We have offices in Australia, Asia, Europe, Canada, and the United States. We have an office here in New York, just down the road. And we have also employees in different clients' offices. So we are basically where we are needed. And traditionally, we have been needed and associated to capital markets because, nowadays time is money. And we are the providers of the world's fastest time series database, which is KDB+. It's not that I say so, it's that it has been tested against our competitors, and it has been proven to provide the fastest and best solutions. So that's why most of the major banks in the world have integrated our technology in their systems, because it allows them to analyze data extremely fast. And time is crucial in the banking world. So one of the reasons why KDB is so fast is its own natively integrated language, Q. And in order to explain what Q is, I'd like to share with you how I first saw Q when I started and how I see it now. So when I first joined the company and I went back home and my friends asked me, "Oh, what do you do, Espe?" I was like, "Oh, I'm a KDB developer, which means I write code in Q." But they didn't know what Q was, so I tried to explain what it was, and I went through all its features. So basically, it's a functional programming language. It's array-based. We cared a lot about time, so we support very different temporal data types, and it has tables as the first class type. It makes easy to manage the data, and it actually integrates its own SQL language, QSQL, which is very similar to SQL or SQL, but it's more intuitive and faster too. So at this point, my friends were like, "Okay, hold on, Espe. What you are trying to tell us is that you are one of these nerds that we see every day on TV, that spend the day in front of several screens, looking at graphs, writing lines and lines and lines of code that cannot be read in just black screens." So at this time, I kind of agreed with them. I mean, the description was fair, and I was happy enough with that. But I've always been more like the kind of Harry Potter nerd. So after a couple of months working with Q, I just became the happiest person in the world, because when I realized that I was actually more like Hermione, because Q is everything I've said before. So these are the features, but it's also extremely fast. And it's elegant and concise, which means that I don't have to go to my computer and spend my day trying to write a lot of lines of code to do very simple things. I just need to go to my keyboard, type a few characters, and everything is done like this. Just milliseconds, you have your solutions, and you don't need lines and lines of code, as I said before. Sometimes you can do things in 2-3 characters. Actually, I was joking with my colleagues the other day. We sometimes play to see who is able to write the shortest code, because whoever gets the shortest code will probably get the fastest solution. So sometimes I'm just like, okay, I have 2 characters, I have slash, and that's all, and I get very powerful things. So it's like, that's magic for me. I don't know why this is happening, but it's doing what I want to do. So every time I go back home now, and my friends ask me, what do you do? I just say, magic. Don't ask me, just magic. And is that what I say that is magic that has brought us in the latest years, as time is also becoming more and more important in different sectors, to move to different verticals and provide solutions not just for banks and capital markets, but also for manufacturing, automotive, telecommunications, space. And as we are moving to these different sectors, some new challenges arise with it too, as it's machine learning. So our clients are asking us for machine learning solution for their problems. They all want to use machine learning. So we need to cope with that, and that's why we went with our machine learning solution last year, and that's why I flew over to California last summer to take part of the NASA Frontier Development Lab, which is a 2-month program hosted by the SETI Institute and the NASA Ames Research Center. It brings together public and private sectors to create an AI research accelerator, which means that in 2 months they gave us 7 different challenges, and we have to find out how to apply machine learning to solve these challenges. There were 7 different challenges. You have in the slides the topics of these challenges. Some of them were split into sub-challenges, but we took part, KX took part of 2 of them. One of the space weather sub-projects. We try to predict when the solar activity will affect the magnetic field of the Earth. So it's very interesting. I think I share in the resources the white paper we have about it too. But I was more involved in the Exoplanets challenge, which, as the name suggests, the aim of it is to find new exoplanets in the solar neighborhood. So how do we do that? Or how do they do that like in NASA? So they have a satellite going around the Earth. It's rotating. It was launched last year in April, and it's a 2-year mission. So it will be going around the Earth for 2 years. And I'm gonna play a video, I think. Yeah. So basically, they have split the sky in 26 sectors. So the satellite will be looking at each sector for 27 days. So it will be taking pictures of the sky at a given frequency. If I don't remember wrong, it's every 30 minutes. So in these sectors, we have different stars, and we have to find out if this star hosts a planet. So it will rotate for these 2 years. First, it will cover 13 sectors in the southern hemisphere, and then it will rotate to the northern hemisphere. And in this way, it also have a very powerful tools which will allow to measure the brightness of the different stars that it's looking at, because that's the way exoplanets are detected. So you have the satellite taking pictures, and then you have a star, and you measure with this tool I mentioned before the brightness of that star for a period of time. So if in this period of time you see that there is a drop in the brightness of the star, that may indicate that you have a planet. It's like an eclipse. But the problem is that it seems easy, but it's not, because there are some other phenomena that could cause this kind of drop in the brightness. We could have eclipsing binaries, which means that this bright is like the intensity of the light is changing because the stars are rotating. We also have background eclipsing binaries, which means that the planet is in a background star, and we can have like solar storms or noise. So it's not that as easy as it seems. So the process is very complicated, but I will try to summarize like the data pipeline very fast. So basically, we have what I said, the images, the satellite is taking pictures, and we have these pictures, and we have to detect the target stars, because not all of the stars that we see in the pictures could host a planet. Once we detect the target stars, we need to detect in the image which pixels represent each star. So, for example, for this star that we have here, the brightness of this star is going to be represented by these 5-6 pixels. So you have to find out that too. And then once you figure out that, you go and kind of zoom the value of the pixels to determine the brightness, and you obtain a light curve. But that light curve, it's noisy. You have a lot of things happening in the sky. You have the satellite itself adding noise, so you have to clean that in some way. So you clean it, remove trends, noise, and everything that you don't want to be there. And then you have the corrected light curve, which is better. It's not as noisy. And in there is when you start to look for planets, more like features of the planets and everything. So when we went to California last year, the satellite was just launched, so we didn't have the actual data, but NASA provided us with data from simulated data from 4 different sectors. And in these 4 sectors, we had 64,000 target stars, signal of a planet or something that could be a planet was found in 9,000, and in these 9,000, they detected nearly 10,000 of planet candidates, because some of the stars could host more than one planet, like the solar system. And then they also found some of the features of the planet. So, for example, the period of the planet, the epoch, the duration, and all these kind of things. But yeah, you do that, but it's still they are not able to filter planets, and they have a lot of false positive. And when I say false positive, I mean this phenomenon I said before. Yeah, the eclipsing binaries or background eclipsing binaries and these kind of things. So we need to filter that, because you want to study stars that could host a planet. So you need to filter that. You don't want to spend time and money looking at the star that it's not hosting a planet. So these are some examples of the corrected light curves. These are some light curves that I chose, and they are not very difficult. There are some of them that are more noisy, but in here you can see different examples of the way they are. So when I was preparing this presentation and some of my colleagues came to my desk, I was like, oh, do you know where the planet is? And they were like, oh yeah, it's here. And any of them said which, like, they all choose different options. They never said the same again. And I was like, no, that's not, like, could be the one in the corner. You have like 2 drops, but it's not easy to say where it is. Actually, when I said, oh, it's in this one, the one in green, they were like, why? It's like, cannot you see the drops in the other one? I was like, yeah, but it's not so easy. So they were all very confused. It was like, why? Explain me why. And I was like, okay, let's use some of the magic I said before. So let's use Q, and let's prepare the data. Q is extremely good to deal with time series and do very powerful things. So we just said, okay, see, let's do that. And after using Q, we got these local views of the light curve. So in here, it's much easier to say, okay, I know where the star is, where the planet is now. Because, yeah, we have these drops too in a few of them, but the ones that are sharper, you know, once you study and you see the different light curves, you know that these are not planets, are the ones that stay on the bottom for slightly longer. So now it's easier to say where the star is. So let's try and let's use machine learning. it seems easy with these light curves now, but it's not. Like, as I said, I chose that one because they were easy to simplify what we had, but it's not easy. And actually, for many years, they have been trying to find solutions to the problem of finding exoplanets. And what they had so far was humans looking at light curves, and not the ones that I showed about the local curve, the ones before, the ones that were noisy. So they spent a lot of time looking at light curves, and you cannot deal with that. You have too many stars, a lot of data. You need to sort that in some way. So it has been tried with a very complex model, which requires a lot of pre-processing. It's very time-consuming. The models take ages to train. So let's try something different. So what we suggested was a Bayesian neural network. But at the beginning, we tried like, okay, let's see, maybe this data is easy. We can try with some other models. So we just said, okay, let's have a benchmark model. Maybe a linear classifier is able to do something. So these are some of the results of the linear classifier. It seems accurate, but it's not, because the proportion of planets are not planets. It's I think it's 80-20, so it's not doing a great job here. And actually, what is even worse is that the precision is very low, which means that most of the thing it detects as planets are not planets, so you're going to spend time and money, as I said before, looking at a star that is not hosting a planet. So you don't want to do that. Like, we all know that money and time are important, and nobody wants to waste it. So we tried, as I said, with a Bayesian neural network, because it also offers more flexibility. We can work with uncertainty, with confidence. So we just wanted to give it a try. And for those who have never heard about Bayesian neural networks, they bring together stochastical models and neural networks, which means that at the end, we won't have a model that just gives us a probability, but we can get a distribution of probabilities. So we can, based on that distribution, do more things. And why do we get a distribution? Because we don't train the weights of the neural network. What we assume is that these weights follow a distribution, and we train the parameters of this distribution. So every time we feed the Bayesian neural network with a data instance, it will get a different value, because the weights of the neural network will be randomly generated using these parameters. So we can play with this distribution and make decisions based off standard deviation, means, or different parameters that we can use. So in order to build the Bayesian neural network, first we need to prepare the data. As I said, we extracted the local view, all these things I mentioned before. But we also had to deal with the proportion of planets and non-planets, because when you are training the network, you want it to detect the planets, and the proportion is low. So you need to do something to avoid the problem of gradient that doesn't update the weights as you want. So we use oversampling, and we had a final proportion 50-50. After that, we have to correct that proportion, but it can be done easily. So we said, let's go with that, and we build a neural network. So in order to do that, we use embed-py, which is Python and Q together. So we just embed a Python process in our database, and then we can provide data in Q, but use the Python models to train to get the solution. So these are some of the parameters we use for the Bayesian neural network. It's not we just wanted to give it a try. It's not a very complex model, but we found out that it was doing good enough. So these are some of the results. We see here in the images like a distribution of one of the planet candidates that we have. So we see that in some of the outputs we had that the probability of being at planet was low, but in general it's high. So we can play with that. The sample of the probabilities, it was like 500, and then we just based our decision because it was giving good results on the mean of the probabilities. If it's higher than 0.5, then we'll say that it's a planet. If not, we'll say that it's not. But you can play with the like standard deviation and everything, because maybe you want to be sure that what is happening, like you want to be all the time high the proportion, like the probability, sorry. So we went with that, and these are the results. So I'm finishing with it now, but just to show a few plots that we extracted, which allows to analyze better the data and see if you're happy enough with your results. So here we have some plots that show this distribution of the probabilities. So on the left, we have the ones that are not planets. So we see that standard deviation in general is not high, and the mean is close to 0. So we say that these are not planets. On the right, we have example of planets. We see that the shapes are what we were saying before, like we have a drop, and then we have a higher standard deviation, but at the end the mean is close to 1. So we say, oh, this is a planet. And well, the last one is not well classified, but yeah, we see that like it changed a lot between 0 and 1. So you can play with these kind of things, and you can probably get better results if you combine different parameters. These are just some other examples of classification of the light curves we had. We see that in general, the Bayesian Neural Network was able to at least classify as planets some of the light curves that you can clearly see that they are planets. So we were happy enough with the results. As I said, it wasn't a very complex Bayesian neural network, so we can tune more parameters and do it even better, play with more parameters, but these are the basic things about it. And that's all. Thank you very much for coming and listening. If you have any question, I think we don't have time, but I will be happy to answer to any question in the breaks. I will be around the whole day. So thank you very much, and if you have any problem, thank you.